Hello everyone, my name is Yongfeng from Tsinghua University, and today I'm going to present our work on in-situ programmable switching using rP4 towards runtime plan programmability. Switch chips have evolved from fixed function switches to programmable switches, and users can write their own packet processing functions. With the emergence of more and more diverse network applications, it is necessary to update the functions of the switch without interrupting the current traffic. That is, give users the ability to customize the protocol flow table and processing logic at the runtime. There are many scenarios that need the feature of runtime programmability. For example, network telemetry or measurement based on real-time network conditions cannot be frozen at the same time, so it is better to make them on demand at runtime. Second, many in-network computing functions are not always needed and are resource-consuming, so it is better to make them hot pluggable at runtime. Thirdly, the change of traffic pattern and the network scale makes it necessary to enlarge or shrink a table's width or depth, provision new tables, or change a search key at runtime. Fourthly, for multi-tenant services, modifications for any tenant cannot affect other tenants. By now, the service upgrading needs to stop all services. Lastly, device updates can be destructive to the states of stateful functions. For example, congestion control and caching. This can be avoided by uninterrupted incremental updates. Next, I will show why the current programmable switch architecture is incapable of runtime updating in terms of protocol, processing logic, and memory. As for protocol, in the figure, four functions need different protocols, so when adding a new function with new protocol, the front passers and the pipeline stages both need to be updated, which can be rather complicated. As the front passers are not in the pipeline, the throughput is influenced by the complexity of the parsing graph. More seriously, we're unable to add new protocols to parse in PISA, as the fields in the protocol are orchestrated meticulously. At the left figure, we can see that the maximum number of ingress and egress stages is fixed and they are hardwired, so the design space is limited. At the right figure, inserting a new function f3 between f1 and f2 requires to reprogram all the affected stages. That is, reprogram the stages after f3, which is time-consuming. As for memories, when adding or deleting functions, processing logic migration in the left figure is migrating L3 to the second processor, means the associated table migration. And if the size of the flow table is too big, there should be more than one processor to implement the function, which decreases the usability of MAUs. Next, I will introduce how IPSA solves above problems in terms of protocol processing logic and memory. We integrate the front parser into the normal pipeline. The function module passes protocols that it will use independently. And when inserting a new function, this architecture can minimize the effect on other functions. Naturally, the processor is composed of parser to pass protocols out, matcher to match fields against the flow tables, and the executor to execute actions. We use the parser, matcher, executor triad as a template skeleton named TSP, so configuring the processor becomes downloading skeleton parameters, that is, what to pass, which table to look up, and what actions to execute. All about are based on offset and length. For example, if we want to use the header length field IHL in IPA4, we should obtain it by IPA4 offset, the internal offset of IHL and the length of IHL. Now, we can configure any TSP with parameters, and then we should know how to insert or delete them in the pipeline. We choose a selector between TM and a few TSPs, and these TSPs can be mounted or unmounted from the select flexibly. For example, if we want to insert function stages, the step is configure the idle TSP then mount the new TSP on the selector and unmount the predecessor TSP. And if we want to delete function stages, migrate the successive TSP parameters forward and unmount idle TSPs. In this way, the range of ingress and egress stages is improved and thus enlarges the design space of ingress and egress pipeline. As for memory, recycling and rebuilding lookup tables are tough problems. IPSA disaggregates the memory from processors to a shared memory pool like DRMT. A crossbar switch is statically configured for each design to provide interconnection between TSPs and memory blocks. Updates on either TSPs or tables may require a reconfiguration of the crossbar. To cope with the scalability, different crossbar types such as segment crossbar, claws, fins, and etc. can be used as a trade-off between flexibility and resource consumption. The overall architecture for IPSA brings the above solutions together. We have upgraded the architecture after this paper. For example, we replaced the selector with interconnection network such as claws, fins, and so on, and the memories are clustered to improve the scalability. As there is no interface in P4 to configure functions and runtime, we designed a new P4 language extension, rP4, dedicated to programming IPSA-based devices. rP4 conforms to Partial Measure Executor Triad, and most components are based on P4. At the right figure, we can see that the function ECMP is initialized by corresponding parameters with the template skeleton. The workflow of rP4 is, firstly, user customizes the base design in P4. Then, with the rP4 front-end compiler, it can be translated into rP4 intermediate representation. With the rP4 backend compiler, the AR can be compiled into target-dependent configurations. In-situ programming can be done in IPSA control plane. Users can download commands and rP4 code snippet, and the rP4 backend compiler translates the runtime requirements and updates the AR. Then, the compiler provides new interfaces for flow entry modification and so on. Here is a use case. After IP lookup, the next hop is determined, and the egress port should be retrieved by the next hop. And now, user wants to add ECMP function. They can write the rP4 code piece and the instruction command. Once the commands are issued, the device deletes the original links with next hop and adds new links with ECMP. In the meantime, the memory blocks next hop is recycled, and the new floatable ECMP is created. We have implemented the architecture in FPGA and a behavioral model named ipbm, like BMV2 in P4, and we have implemented the compiler and control plane interfaces. As for updating time, the compiling time and configuration loading time of IPSA are about 3% to those of PISA in Table 1. In the latest experiments, the pipeline halting time is 2 to 3 orders magnitude lower than PISA. The runtime reconfiguration brings resource overhead, which is acceptable. As for throughput in FPGA implementation, the decrease in IPSA is due to the limitation of FPGA multi-die solution, which can be improved to the same as PISA in ASIC. Because idle TSPs can be set in low power mode, when fewer processors are used, IPSA can save more power. IPSA and rP4 advance the state-of-art of the programmable networks by introducing a new switch chip architecture and a new programming language based on P4. We will continue to improve the work from multiple fronts, such as architecture improvement, hardware implementation efficiency and performance, update procedure for truly uninterrupted runtime updates, compiler for simpler programming and better resource mapping, innovation applications on it, and etc. We hope that the community can join the force to realize and perfect the vision. Thank you for listening, and I'm available for your questions.